Okay, so here in this particular video, we have a cannonball that shot off from a cliff of some unknown height. So in this particular animation, it shows that the horizontal component of the cannonball is 60 meters per second, and it also shows, if you watch it when it reset, that the vertical component initially is also 60 meters per second. And then it wants us to find all these different parts, A, B, C, D, and E, and it wants us to use G as negative 10 meters per second square rather than 9.8, which is just for the sake of easy calculations, okay? All right, so let's do it. Let's knock out part A, B, and C, okay? So part A asks us to find the initial launch velocity. In this particular animation, it just shows the two components, Vx and Vy, as time lapses. But here in part A, it's pretty straightforward. It wants us to find the initial launch velocity, excuse me. So therefore, all we have to do is set up Pythagorean theorem. The animation gives you the horizontal component initially is 60 meters per second, which is given in this still image here that I copy and paste. And then the vertical component is upward, also at 60 meters per second. So you know here in this animation, the initial velocity in the horizontal component is 60, but the initial velocity in the y direction is also 60, which is kind of nice. Okay, so all we have to do is you really use Pythagorean theorem to find the initial velocity vector, which is the diagonal. All you have to do is use this function, which is Pythagorean theorem. All right, so therefore, all we have to do is plug in the values that we know. Vix here is 60. We're going to square that. Viy is also 60. We're going to square that. And that's going to give us Vi square. So if you do 60 squared plus 60 squared, that'll give you 7,200. And then this is Vi square, but it wants us to find the initial velocity. So all we have to do is square root both sides to do that. Just radical Vi square. That'll get rid of the square. And then the radical of 7,200 would give you an answer of 84.85 meters per second. And because it asked for initial velocity, I included the direction here for you. Here, I'm not going to do any math just because this is kind of easy. Your horizontal side is 60, your vertical side is 60. So for a triangle, that is 45 degrees because the two legs are equal. Okay, so that's why my answer here has a direction of 45 degrees northeast. So if you look in the still diagram here, this is what I just found. The initial velocity, which is that vector that's in between your vertical and your horizontal. So that value is going to be 84.85 meters per second. And again, because it asks for velocity, I include the direction, which is 45 degrees because this is a square pretty much. All right, so that's that. Now let's do part B. To do part B, it asks us to find the speed of the cannonball at the top of the trajectory. So all we have to do is use Pythagorean theorem again, and we just have to apply it appropriately. Okay, so here I have the still image here. If you watch the animation on the screen as it falls, or it gets shot up and then it turns direction and it starts falling down. Here in the still image, at the peak, I like to point out that the only velocity that is left is Vx. So Vy approaches 0 at the peak, while Vx remains constant, because for these types of problem, Ax is 0, so therefore Vx stays the same. So I can just apply Pythagorean theorem at the peak. Well, at the peak, I know that Vy is 0, so I'm going to cross out my Vy term. My Vx is still there though, okay? So the velocity is not 0 at the top. The velocity simply takes on the behavior of Vx because Vy goes to 0. So therefore, all we have to do is plug in really value at this point, which is pretty straightforward. But here you notice V at any time square is equal to V of x squared. And this happens only at the peak. So therefore, we can just cross out the square there. Or you can square root both sides. I just like to cancel out the square there because it appears on both sides. That leaves us with the statement V at the peak is just Vx. Okay. So therefore, we know that Vx is 60 because it stays constant. So that is our answer. So this part B is pretty straightforward. So the speed at the peak is simply Vx, which is 60. And it says speed, so I won't include direction here. So the answer is just 60 meters per second. All right, let's do part C. Okay, part C asks us to find the time that it takes to reach the peak. Well, to find the time that it reached the peak, I can simply apply my acceleration function in the vertical direction. So here instead of A, I just replace acceleration with G, which is acceleration due to gravity. Why do I want to do this? Well, I want to do this because I know certain information that's super useful. I know that anytime it sits at the peak, I know that my final velocity in the vertical direction, aka VFY, has to approach 0. Okay, so therefore I can cross that term out. Well, here we're solving for t, so I'm going to flip-flop t and g. Just do a little algebra here. Move delta t up, move g down. So therefore, change in time is equal to negative VIY divided by g. But VIY here is given in the animation. VIY that I'm circling back and forth here, if you watch it for it to reset, or if you look at the middle still diagram here, at times equal to 0, you know, VIY is 60. So I can just use 60 meters per second. Okay, and then here it says to use g as negative 10 meters per second square, so I'm just going to use negative 10 meters per second square. So as you can see here, 60 divided by 10 is just going to give us an answer of 6 seconds. So it'll take 6 seconds for the object to reach maximum height, or in this case, the peak. All right, so that's our answer for part C. Part D and E, not too bad. Part D here asks us to find the horizontal distance traveled after 12 seconds. So if I can redirect your attention in this middle diagram here, I gave you a still image to kind of help you visualize. Well, I know that it took 6 seconds to go up from part C, and therefore this part asks for 12 seconds. So due to symmetry, watch my cursor, it's going to take 6 seconds to go to the peak, and then from the peak it's also going to cover another 6 seconds. Therefore, this x that it wants me to find is kind of nice, okay? So this x that it wants me to find for part D is kind of nice because it's symmetrical. It's not above or below where it falls. So delta y here is 0. All right, so at 12 seconds, I know that it came back to the same vertical position, aka my delta y is 0. So that's going to be useful in terms of using different strategies to solve for this problem. All right, let's do it. Part D, I can simply use delta x is equal to vx times time. Again, the 1/2 ax t squared is 0 because ax is non-existent for these types of problems unless otherwise stated. If not stated, you can assume ax is 0. All right, so vx is 60 in the diagram. Again, the still image here tells us that vx is 60 and it stays constant throughout, so it doesn't really matter at what time. Vx is 60 meters per second. Here, I just plug in t as 12 seconds because part D asks us the horizontal distance at 12 seconds, so I'm just going to use 12 seconds. Therefore, we can simply multiply that 60 and 12. That will give us 720 meter. Okay, and since it asks for distance, which is a scalar, I'm not going to include direction for part D. But the other way to do it, if you happen to know the range function, and this one is really helpful for this particular part. Again, I recognize that at 12 seconds, the cannonball comes back to where it was originally along the vertical axis, aka my vertical displacement is 0. If my vertical displacement is 0, I can use the range function to find my horizontal displacement or distance. Here, this says vi squared sine 2 theta over g. Well, we already know vi from part A or B, one of the parts that I found earlier. We know the initial velocity is 84.85. We're going to square that. And we know here the angle of launch is 45 degrees, again, because Vx is 60 to start. Vy is also 60 earlier when I gave you the still image. So 60 and 60 makes a right triangle that's equal sides. So therefore the angle is 45. Here sine of 2 times 45. So 2 times 45 is 90 degrees. And if you put in sine of 90 degrees on your calculator, hopefully you're in degree mode. If you're keeping up, it would just be 1. Okay, so therefore here I just took 84.85. I'm going to square that. It's going to give me 7,200, which is what we got earlier before we square root to find the answer for VI. So if you need to rewind the video to see what I'm talking about, the 1 comes from sine of 90 degrees. Sine of 90 degrees on your calculator in degree mode will give you a value of 1. Here, G is 10 meters per second square. You notice here I just plug in 10 G as positive because here this range functions allow us to find the distance going left or right. So whether you need to include direction or not, that all depends, whether an object is being projected to the right or left. but it doesn't change the outcome if you plug in negative. It will just give you a displacement going left instead. But here it asks for distance, so I'm really not going to care about the direction here. All right, so therefore, if you plug all this in your calculator, you should get a value of 720, which, as you can see, is what we got to the left side here, just using our kinematics function. Okay, so use whatever strategy you want. Just make sure that you're careful with all your trig and calculator work. All right, let's do part E. Part E asks us how far below the cliff, aka the launch, will it fall after 17 seconds of flight. So we know that based on this GIF here, at 12 seconds, it's gonna go all the way back to where it was, right? And then it's gonna keep on falling. Okay, so it wants to know how far below. So here, because it asks for how far below, I can just use my kinematics displacement function in the vertical direction. This is super useful. So my VI here, I'm just going to plug in a positive 60 because I'm going to start at 0 second and go all the way to 17 seconds. So my VI initially at times equal to 0 60. Time here is 17 seconds because that's what part E wants. And here I just plug in G. I plug in -10, and then time here is 17. I want to square that. Okay, so if we simplify our calculator work here, 60 times 17 is 1020. And then if you do 1/2 times -10 times 17 squared, that will give us a value of -1445. Okay, so if you do your calculator work carefully here, we have a positive number at a larger negative value. So the sum here is going to be a negative value of 425 meters. Now, well, which makes sense. It fell 425 meters below where it was after 17 seconds. But since they asked for how far, I would just give the answer as 425 meters. Okay, how far usually refers to distance, and distance is a scalar. So I would just say that it fell 425 meters. All right, the other way to do it, using the same kinematics equation, just using a different reference point, and that is, well, in the still diagram, I know that it took 12 seconds. Watch my cursor. I know it took 6 seconds to get to the peak. I know it took an additional 6 seconds to get down to here. So here is already 12 seconds, okay? So to complete this first horizontal distance of x, it took 12 seconds, but it wants it 17 seconds, so I know it's gonna fall an additional 5 seconds. I can use this point that I'm circling as my reference point, okay? So if you like, try different reference points just to help you, build confidence here. I want to use this as my reference point. If I use that as my reference point, my VIY is actually -60 because now the vector is upside down. So at this point, the vertical vector flipped because it's now on its way down. So initially at times equal to 0, VY was +60. But by the time it reaches the same vertical position on the way down, its velocity vector in the y direction flipped. So hence -60. Time here though is only 5 seconds because I'm starting at 12 seconds. From 12 to 17 seconds is a difference of 5 seconds. Okay, so that's where the 5 comes from. And really everything else on the right side stays the same, except notice here at the time it's only 5 seconds. Why? Because I'm looking for the distance that it fell. So really I can reference here and just kind of measure the distance that it fell down from there, which is the same distance that fell down from here if you want to start at 0, which is what I did originally. All right, so if you do that on your calculator, -60 times 5 is -300, and then 1/2 times -10 times 5 squared will give you -125, and then as you can see here we have a -300 plus another -125, which gives us a sum of -425 meters, which is the same answer as we got in the previous strategy when I started from 0 second and go all the way to 17. So pick a reference point, but as long as you're consistent with your values, everything should work out. Okay. All right. Stay nerdy. I hope that helps. Don't be whack.